No mai hoki mai katoa. Welcome back to LCA Day 2. We have Angus with us. Angus is a computer science student at the Australian National University. And today he's going to be talking to you about the Memory Management Toolkit, the MMTk. It's an open source project and a runtime agnostic garbage collection framework being developed by researchers at ANU. This is Angus' first time attending and talking at LCA, so go easy on him. No mai Angus.
Thank you very much. So, good day everyone. Lovely to be at LCA this year, and I hope you all enjoy. Before we start, I would like to acknowledge the Wonnarua people who are the traditional custodians of the land from which I'm speaking. I'd like to acknowledge and pay my respects to the elders past, present and future, and I'd like to extend those respects to any Aboriginal or Torres Strait Islander people present with us today. So the story behind this talk begins at ANU, where I'm a student. This talk was about a research project that I did with Professor Steve Blackburn over the summer of 2020 and 2021. The project was about integrating the Ruby programming language with MMTk, which is this garbage collection framework that's been developed by researchers and students at ANU. It's been around for about 15 years or so at this point. And the reason why I'm giving this talk is because I learned a lot along the way about garbage collection, how Ruby works, MMTk, all these things, and I thought it would be really interesting to share with you some of the things I learned along the way. So the plan is we're going to start with a look at Ruby's existing garbage collector and how that works. We're going to look at a bit of the memory model, some of the problems that exist with the garbage collector at the moment, and what the Ruby team has done over time to try and fix those things. We're then going to have a look at MMTk and see how it can try and solve some of the ongoing issues that have been happening. And we're going to have a look at how MMTk works and how you can connect it together to other languages. And we're going to continue on to how I went about integrating MMTk and Ruby in my summer project. So let's start with Ruby's memory model. So Ruby uses fixed-sized objects of 40 bytes each. So as you can see on the bottom left-hand side of the slide there, we have a single object, 40 bytes, has a 16-byte header that has some flags that are used for keeping track of various type and various state about the object, and the class pointer to whatever the parent class of that object is, and the class of that object is, and a body which can store up to 24 bytes of information. Now, obviously not all objects are going to fit in that 24 bytes of space. We can see in this case our string has managed to fit, but on the right hand side here we have an array that's too big to fit in that slot. So what Ruby does in this case is it allocates extra space using malloc off to the side to store that data. The main objects themselves, which Ruby calls slots, are stored in heap pages, which contain 408 slots. Now, note that this definition of page is different to the use of the word page in operating systems and that sort of thing, so just want to alleviate any confusion there. So now that we understand how Ruby stores its objects, how does Ruby actually do garbage collection and automatic memory management? Ruby uses what's known as a mark sweep garbage collection, which has two phases, a mark phase and a sweep phase. In the first half, the mark phase, we determine what objects are reachable from the roots of the program, where the roots are like objects on the stack, local variables, global variables, anything that the program can access at a particular point in time. From these roots, we trace down into the heap, identifying what objects are reachable from those roots. We mark those objects using a mark bit, as we can see down the bottom here, to identify that they are reachable. We then recursively search those objects and find objects that they point to and mark those, and so on until we've searched the entire heap. This process is called marking. Now, this process has identified all objects that are reachable from the roots, which means anything the program still could be using. So we know these are not safe to garbage collect. But any objects that aren't in use, like those two grey ones that aren't marked, it is safe to collect them because they're not reachable from the program, Therefore, the program cannot access them in any way, so it's safe to reuse them. So after the mark phase is done, we go through the sweep phase of actually collecting the objects. We start by looking at the mark bit of each object and identify whether or not it should be collected. Here we have an object that's marked, so we should keep it. Here we have a free slot, so we obviously don't need to do anything. We've got 2 more objects here which are marked with a 1 in the mark bit, so we want to keep those. And we just unset the mark bit as we go along so that when we do another garbage collection cycle later, they're all ready to go again. Now, as we can see here, we have an object that has no mark bit set, but it does exist, which means it's not reachable, therefore it's garbage, so it's safe to collect it. And finally, we can continue through the heap doing a similar strategy, keeping any objects that are reachable and unsetting the mark bit, and freeing any objects that aren't reachable. So this mark sweep garbage collector has a couple of main problems. The first one is that it's what's known as a stop the world garbage collector. This means that you can't have the GC running at the same time as the Ruby code. When your Ruby code runs out of memory, it needs to stop. The GC will then run in entirety, and then the Ruby code will continue. Now, this caused Ruby to be known for one particular thing earlier in its lifetime. And that was long pause times. Particularly, these would have a huge impact on latency of the program. In fact, this issue is so bad that GitHub, which is one of the major Ruby users today, and historically, they would disable Ruby's garbage collector whenever they were processing a web request, and then they'd re-enable it later once it was done to avoid a GC cycle from happening in the middle of a request, because they were finding it was impacting their 99 and 95th percentile latency too much. They did remove this in 2018, though, due to some improvements that have been made over the time to Ruby's garbage collector. The first of which was the Ruby team implemented lazy sweeping. So remember how we had 2 phases, mark and sweep. The sweep phase, we don't have to do it all in one go. We only have to go as far as to reclaim enough memory to actually continue with the execution of the program. So as we can see here, you execute, do the full mark phase, and then only sweep a little bit. We can continue executing and only sweep little bits whenever we need to. This doesn't actually reduce the amount of time taken by the garbage collector in total, but it does amortize it over the lifetime of the program, which reduces the average pause time. The second thing that was introduced was generational garbage collection. Now, generational garbage collection is relies on one of the most important observations in the garbage collection literature, which is that when you allocate a whole bunch of objects, the majority of them die quite young. They don't survive many GC cycles. So what Ruby does is, and the reason why this is very useful is because these small amount of objects that survive past an initial cycle, they have to be retraced every single time you go through the mark phase, which is a bit of a waste of time. So what you can do is separate the objects into 2 generations. An old generation, which consists of objects that have survived some collection cycles. In Ruby's case, that's 3 cycles that are needed. And you have a young generation, which contains newly allocated objects. And then during a minor garbage collection cycle, you only check the newly allocated objects, because most of those will die pretty quickly. And then only every now and then, when you're totally out of space, you do a major garbage collection cycle and do the old things as well. This both improves the throughput and reduces the pause times of the GC. And the third improvement that's been made over the years is incremental marking. So you know how with the lazy sweeping, we were able to break up the GC pause time into multiple smaller steps. By implementing a tricolor marking algorithm, Ruby was able to break up their garbage collection time into the mark phase into smaller parts as well. And this overall had another great effect on reducing the average pause times, although it doesn't actually improve the throughput. The other major problem that this collector has is that it's a non-moving collector. When you allocate an object in a particular place, it's never going to move again. It'll just stay there until it's eventually freed by the garbage collector when it becomes unreachable. Now this causes fragmentation, because once we collect all the stuff in between, we have all these random old objects dotted around that aren't actually using as much space as they have allocated. So this overall inflates the memory usage of the program. Now, Aaron Patterson, who you can see on the bottom right hand corner there, he's been doing some really great work on Ruby's GC and implementing a mark compact algorithm, which essentially compacts down all the objects into fewer heap pages. As you can see on his slides there from his excellent RubyConf 2020 talk, there is a substantial saving in memory usage thanks to this algorithm. However, work on this is still ongoing. Although it does support automatic collection, it's turned off by default due to performance concerns. Now, obviously this has been going on for a while, but what have you heard from a GC expert that these techniques, for instance, generational garbage collection, which was first proposed in this paper by Libben and Hewitt, was first proposed back in 1983. The mark compact algorithm dates back even further, 1974. You're probably wondering, why has it taken Ruby so long to implement these techniques that have been known for a long time? The answer to this is in many ways simple and obvious. Garbage collection is hard. Building GCs is hard. You've got to have specific domain knowledge about how garbage collectors work. It's easy to learn the basics about basic algorithms like mark sweep, but for more complex collectors that can require quite a lot more reading and understanding. You've also got to make sure you're focusing on correctness. If a GC has a bug and collects an object that's still reachable, that can have huge ramifications on the correctness of the program. Later on, some programmer could try and access that object, and suddenly everything segfaults and grinds to a halt because the garbage collector has a bug in it. This would be a huge problem, as you can imagine. And finally, performance requires specific domain knowledge to improve with GCs. But what working on this project has really taught me over the summer was that it's not just that building GCs it's hard, it's the fact that building GCs into production-grade language runtimes is just so much harder again. Let's take a look, for instance, at some of the major VMs and see how big their GC runtimes are. OpenJDK, 100,000 lines. .NET, 63,000. V8, 53,000. Ruby is a little bit of a baby in comparison, only about 11,000 lines. But there's still a huge amount of complexity in these systems. And this isn't representative of the total amount of code involved, because GC often seeps into all the other different parts of these systems. There's so many things that you need to worry about. From implementation concerns like concurrency. You can imagine if you had a garbage collector that moved around objects over time. If you're doing that while a programmer is using the object, that could cause big issues if that object moved while it was still being used. You've also got to worry about integrating the GC into the just-in-time compiler if the language runtime has one of those. You've got to modify the bytecode that's generated by that compiler to hook into the garbage collector. And over time, as language runtimes become older, software engineering issues start to be a problem as well. You get abstraction leakage, where parts of the runtime assume that there's a fixed memory model using a fixed garbage collector. They assume how it will work. For instance, in Ruby, it's assumed that the garbage collector works on 40-byte slots. Nowadays, they've discovered that 40-byte slots are bad for locality, CPU cache locality, because occasionally you'll have an array allocated totally separately, and this pointer update often causes a cache miss. So they want to improve locality by allocating them all in one giant object, but due to all the assumptions in the runtime about how the garbage collector works, this is really difficult because so many things have undocumented assumptions. You also have programmers using the GC for things that aren't necessarily GC-related tasks. For instance, the GC is often used to close and flush files after they're no longer accessible and that sort of thing. And finally, one other problem is backwards compatibility. In Ruby's case, C extensions are a really large concern. So Ruby gems, which are like libraries from Ruby, they can implement their own C code, which hooks into Ruby's API to perform tasks faster. However, this C API is fixed. It was built a long time ago in Ruby's history, and programmers all assume how the GC works. So when we want to build new garbage collectors, it's really difficult maintaining compatibility with these gems. And we can't just drop compatibility or expect them all to be updated, because then so many libraries would break. And all of these software engineering problems cause a huge number of social factors that are really difficult to deal with. First of all, it's scary making such huge changes to the language runtime. If you saw a patch being made to your programming language of 100,000 lines, you would be a little bit hesitant to merge that without lots and lots of work being spent to review that, and not everyone has the time and effort to review those changes. And because of this, there's a huge amount of inertia behind these language runtimes, because it's very difficult to change them. So we find that complexity is impeding innovation on garbage collectors. The literature has lots of new innovations and techniques that are out there, yet not many of them are actually implemented into the production grade systems that we use every day. So what can we do to solve this problem? Well, this is the aim of the Memory Management Toolkit, which is being developed by researchers at ANU. It's an open source, runtime agnostic garbage collection framework. It provides developers with a large library of high-performance GC algorithms, ranging from the good old tried and tested ones like, Semispace, MarkSuite, MarkCompact, all the way to higher-end, cutting-edge, high-performance collectors like IMIX. It was originally developed in the early 2000s for JIKES RVM, which was IBM's research virtual machine for Java, by Professor Steve Blackburn, my supervisor, along with Perry Cheng and Catherine McKinley. In recent years, it has been rewritten in Rust, with the idea that we can enable interoperability with not just JIKES RVM, but also other language runtimes, and that's the idea of my project today. These GC algorithms are exposed behind a single bidirectional API. Now, the advantage of this for language implementers is you only have to implement this API once, and then in future, you can benefit in future from any and all improvements that occur to these garbage collection algorithms. So all these software engineering challenges that we have that I talked about beforehand, yes, we can't make them disappear, but if we go through the hard work of implementing interface for a garbage collector once, we won't have to deal with these problems again in the future. So this is really powerful and enables long-term innovation on GCs. MMTk is also really helpful for garbage collection researchers and just anyone in general who wants to build a GC. It provides a composable framework for building new GCs, so components of the software that are reused really frequently, like allocation, or bump pointer allocation, or copy spaces, or these sorts of things that are common to many garbage collection algorithms, they're already there, and you can just compose them together to create brand new collectors. It abstracts away the complexity because it's behind this API, which means that GC researchers can focus on the thing they know best, GCs, and they don't have to worry about all of those software engineering details that I talked about beforehand. And possibly most importantly, it enables apples-to-apples comparisons between different garbage collection algorithms running on the same or even different language runtimes. So, how do we actually go about implementing a language? MMTk into a language? Well, we create what's known as a binding, which consists of two different parts. The first half of the binding is conceptually closer to the language runtime. In this case, it's Matz's Ruby interpreter, MRI, which is the most commonly used interpreter for the Ruby programming language. And on the right, we have MRI-specific MMTk code, which is conceptually closer but separate from the MMTk codebase. The idea is that the language runtime in MMTk should remain completely agnostic of the garbage collection algorithm being used and the language that those garbage collection algorithms are running on. And then the binding contains all the details that hook these things together. So whilst it may be possible to perform a generic allocation call from MRI straight through to MMTk, these bindings allow us to do smarter things. Like we can optimize the fast paths by only calling into the binding itself and then running code that's specifically tailored for the combination of Ruby and MMTk. And then in exceptional cases where it's difficult to optimize the code, we can call out to MMTk proper, which has all of the relevant logic. And similarly, this works back in the other direction. We may scan an object and the binding can then know how to read all of Ruby's objects and identify what pointers they point to. what objects they point to. And then over time, the idea is as we build up bindings for all these programming languages, all the programming languages will be able to benefit from MMTk, and MMTk and GC researchers will be able to benefit from having production-grade integrations with language runtimes. We currently have officially supported runtimes for OpenJDK, JAX-RVM, and V8, and there's currently integrations in progress for Ruby, Julia, GHC, with the Glasgow Haskell compiler, and the .NET framework. So how do we actually go about integrating MMTk into Ruby specifically? Well, this was my project that I was working on over the summer of 2020 and 2021. Now, it may seem a little bit confusing, but the first thing we do is we get rid of the garbage collection altogether. We build what's known as no-GC, a garbage collector that doesn't collect any garbage. Instead, we just make all these allocation calls, and over time, they build up and the memory is never freed. Now, that may seem a little bit confusing. Why are we just chucking out all the things that exist and making something that's objectively worse? Well, as I said earlier, there's a huge amount of complexity in integrating with language runtimes, all those software engineering issues that I talked about earlier. And as you can see, MMTk has to have a large API in order to work with a variety of different garbage collectors. But by starting simple and starting with no-GC, which only needs to allocate things and initialize MMTk's information, it makes the task a lot simpler to start off with, and we can slowly build confidence in working with Ruby's code. Over time, we can implement larger subsets of the MMTk API, and as larger subsets of the API are implemented, more and more garbage collection algorithms can be used. And eventually, once all of the API is implemented, all of the GCs within MMTk should be accessible to the language. So, what are the steps involved with no-GC? Well, the first step is we need to disable the existing garbage collector in Ruby. Thankfully, this is relatively easy because Ruby provides a method directly to programmers even that they can disable and enable the GC. So we just call this and then stop the GC from being enabled ever again. Obviously, if we had Ruby's GC running at the same time as MMTk's GC, that would cause a whole lot of correctness issues. The second step is we need to initialize some MMTk metadata. Once again, relatively easy. We need to figure out early on in the VM startup where we can hook in and form this connection between Ruby and MMTk. And the third step, which is the most time-consuming of all of this, is finding every single allocation call within the Ruby runtime and hooking those out and replacing them with MMTk calls. This constituted several weeks worth of work alone. I needed to build an understanding of Ruby's VM, which is difficult when you're coming in as a newcomer, and in general is difficult because there's often like some abstraction breakages. Like for instance, because Ruby uses separate areas to allocate the objects themselves, which are allocated in the heap, and the larger sections of memory that are used to store the overflow space, there was some issues here. While the Ruby heap was really easy to fix up because all those objects are allocated through something known as through a function known as newObjectOf, replacing the elements that malloced separately was a little bit harder because Ruby uses malloc throughout its code base, not just for allocating these side object data, but also VM internal information like thread data, the stack, and that sort of thing. So now that we've done that, we've got it working, right? Well, no, of course not. We're programmers. We know when you compile something for the first time, it's never going to work. But this was a really interesting failure that I wanted to talk about. So what I found was that it was this relatively simple test case. It was doing some stuff, printing out some data, so then that data could be piped to a file, and it could be compared against a master version of that file and check that Ruby is operating correctly. And this test was failing because no data was coming out, and I was very confused by this. And so I wrote a simplified version of the test to see what was the issue. So I just created, a hello world program, then run that program. Cool, seems to be outputting stuff just fine. But then when we pipe the output to a file, redirect it to a file, it doesn't work. There's no data sent to that file. It's empty. So what's happening here? Well, after spending quite a bit of time looking into this, I discovered it was something to do with the way that how Ruby flushes file objects. So Ruby detects when you're redirecting to a file and behaves differently. When you're going directly to the terminal, it more aggressively flushes the output so that you see it faster. Whereas when it's flushing to a file, it's less aggressive and only does it in chunks. Now, this in and of itself I didn't think would be an issue because that has nothing to do with the garbage collection algorithm. It should have happened anyway. And in larger tests I found that it did sometimes work and sometimes not. And it wasn't until I eventually tracked down this code that I figured out the answer. So this is part of the VM shutdown code. So when the Ruby program is finished running and it's about to close and exit the program. As you can see here, it forms a list of these things called a finalized list. Now, this has to do with finalizers, which isn't actually a GC topic, but is often grouped together in the GC implementation. Finalizers are a piece of code that's run when is something that the programmer can register to run, a piece of code, when the object is no longer reachable. In other words, it's eligible for garbage collection, but before it actually collects. This is commonly used for this specific case of flushing files, closing file descriptors, that sort of thing. And as we can see, at VM shutdown, it loops through all of these file objects and runs that finalizer. Now, this wasn't something we were expecting to see because this isn't necessarily something that's usually grouped into GCs. And, oh yeah. Sorry, I've just forgotten what I was saying. And so these finalizers weren't being run because they relied on the GC and I just replaced the GC. So this is relatively simple to fix, but an illustrative example of some things that can happen just by removing the GC that you don't really expect to occur. Now, another thing we considered was a potential optimization, that is thread local allocation buffers. So you can imagine in a VM that supports multiple threads, like V8, you may have allocation calls happening at once. And because these often require locks to be acquired and that sort of thing, there can be some contention that occurs. And this can slow down the program. So a common practice when integrating with MMTk is to use what's known as thread local allocation buffers, where instead of always calling out to MMTk, we acquire just a buffer for that thread specifically, and we allocate into this buffer whenever we need more space. And then when the buffer is completely full, we can call out to MMTk via the slow path. This dramatically reduces contention and improves performance in multi-threaded VMs. However, we decided this wasn't a concern in Ruby because Ruby has what's known as a global VM lock. If you've used Python, you've probably heard of the GIL, the Global Interpreter Lock, and Ruby's GVL is similar to this. It means that only one thread can execute at any given time. And because of this, the allocation calls should never collide, and hence there'll be no contention. So we chose not to implement this. We may investigate it further down the line. So, now that's all that's finished, let's get a little bit of a demo. Right here I have a terminal on a web browser. What we're going to do for the demo is we're going to create and run a Ruby on Rails application. If you've heard of Ruby, it's probably because you've heard of Rails and want to use Ruby on Rails. So, as we can see, we have Rails installed, which in and of itself is a challenge because Rails relies on very many gems that use C extensions. So it's great that we've managed to maintain compatibility with C extensions, which is really important for adoption of this project in the future. So now we can run Rails new and create a basic application. It's doing its thing, checking that all the Ruby gems are present, which are like their libraries. It's generating all the pages and basic framework of a Rails application. And if we cd into the demo directory, we can see we have our basic Rails thing as we expect. And if we run Rails server, we can start up fully functional web server running on MMTk. Whoops, my apologies. And ta-da, we have Rails running. And as we can see down here in the terminal, this is running on MMTk Ruby. Now, there is a downside to this implementation, which is inherent to the fact it's a no-GC. If we have a look at htop and run a script in the background to spam our server with lots of queries, we can see that the memory usage of this server is monotonically increasing over the time. And that's obviously not good. So what can we do about this? Well, we need to implement new allocators, which is a story for another day. So, my apologies for the audio issues there, by the way. You're probably wondering, do you have any performance results? No, sorry. Because MMTk implementation so far is just using no GC garbage collection, doesn't collect any garbage, this would be a totally unfair comparison, so no point showing you any performance results. The second thing you're probably wondering is, what did we actually achieve by doing this? At the end of the day, my project gutted Ruby's GC, replaced it with something that's barely functional, well, functional, but doesn't collect any memory, so it will crash on any system running an actual program. So this may seem like a waste of time, but we have achieved quite a lot in this project. The first thing is that we've begun to build a GC interface for Ruby. Because Ruby's GC is so tightly integrated at the moment, the code changes that are made to the Ruby source code will enable not just MMTk to make use of that, but also anyone else who wants to try and build a GC for Ruby. It also lays the groundwork for higher performance collectors, which I'll be discussing in a moment. And finally, for the MMTk project, we built a porting guide, so if anyone else wants to build their own integration with MMTk, they have this handy guide that you can follow. So what's next? One of the team members, Kunshan Wang, incredibly capable, will be following on with this project and continuing it. His plan is to implement the API necessary for MMTk's mark sweep collector to run. The reason why we've chosen to target this collector is because, well, A, it's similar to what Ruby already has, so there should be less compatibility concerns, and also because it doesn't move objects, which Ruby doesn't really do much at the moment, so to improve the ease of implementation. And then after that, he's going to move on to Imix, which is a high-performance garbage collector that was actually originally developed in MMTk and discovered. And Kunshan's going to be continuing on with this project, which is really fantastic. So before I finish up, I would like to say a huge thank you to the entire MMTk team, Steve for his guidance, along with the rest of the team for helping me when I was having technical issues and teaching me a lot about GCs and that sort of thing. I'd also like to thank Chris Seaton from Shopify, who was really helpful in guiding me through the Ruby codebase and a lot of tiny issues that can be really difficult to figure out if you're not already familiar with the codebase. And also I'd like to thank Ruby's main GC developers for their incredibly helpful technical writing, which was very helpful for understanding Ruby's GC. So that's all I have for today. I have put up this link, which has a copy of the slides and some links. Unfortunately, I had some technical difficulties uploading it just before the presentation. So there's a minimal subset there, and I'll be uploading more over the course of the day. But if you're watching the recording, it should be fine. If you're interested in learning more about MMTk, I've put links to the website and our GitHub page there. There's also our Zulip channel, so if you want to come and have a chat, would be happy to help out. Please do reach out if you're interested in learning or contributing. And finally, if you want to get in touch with me, my info is on the left. Thank you very much, everyone, and I hope you've learnt a lot about Ruby and garbage collectors. Oh wow, 10 minutes under as well.
So good. We have a couple of questions, so we can use that 10 minutes up to get some more quality information out of you, Angus.
Yeah, sure.
So, first question, is there any critical incompatibility with using something like MMTk with Raptors, which make Ruby sort of actually multi-threaded?
I'm not particularly sure on this one, so my code is based on Ruby 2.7, which I believe was before Raptors were introduced, I think. So I didn't really have to deal with those too much, but we'll see as the project progresses whether or not that'll have any major incompatibilities. But Ruby is designed to support multi-threaded VMs. So MMTk shouldn't have any compatibility issues. It's just a matter of whether Ruby expects its GC to work correctly in this case that we'll need to worry about.
Yep. Someone just commented, yes, they were added in 3.0. So
yeah, cool. That makes sense. Yeah, I started this project about a week before 3.0 released, so unfortunately that's not included in the current code, but it has been rebased to 3.1 now, I believe.
Okay, next question. What was the biggest gotcha you discovered while learning how Ruby's GC works?
All of the innovations that happened over the day were a little bit difficult to discover because they aren't documented that well, but once I found the original documentation for like the generational collector that they've implemented, that was really helpful because it turns out some of those features that they implemented for these previous improvements will actually be useful in the future for integrating MMTk, stuff like write barriers and that sort of thing that are commonly used in garbage collectors. But probably the biggest problem I had along the way was that finalization issue that I was talking about. Whenever you're developing something and you can't stick it through DevTools because that constitutes piping it to somewhere else, and hence the VM behaves totally differently to the case that you're trying to debug, that understandably makes debugging pretty difficult.
Cool. And one more. It's all kind of rush in at the end. Is there much interest in taking the GC abstractions you've done to the upstream project?
Yes, that is something that we have considered. This project, we did do a little bit of collaboration with Shopify, and once we've got a bit more stable, the idea is hopefully we'll be able to put it in production at Shopify to see how well it runs, and then once we've got a bit of proof of seeing how well it works and we've got an actual garbage collector implemented like Mark Sweep or Imix, because currently it doesn't actually collect any garbage. Once we've got that, we might submit a patch upstream into Ruby, and then other people can benefit from our changes.
Cool. I also have a question of my own, just because we've still got a little bit of time. So I'm not Ruby. I mean, last time I used Ruby was Rails, and it was pre-version 2 at uni years ago. I do work a lot with OpenShift Kubernetes, so Ruby is not particularly common in Kubernetes in terms of workload environments. How do you see kind of the containerized workload interacting with some of the garbage collection stuff in MMTk?
Hopefully that's an abstraction, because these are different levels of abstraction, we probably won't have to worry too much, because this is all within the language runtime itself. Any container that can run Ruby should be able to run MMTk. But it would be interesting to investigate if, because MMTk is common code, if there's any way that MMTk could be built to have multiple instances that use the same threads to collect code across multiple different languages. I don't know if that's something that could be explored or not.
Yeah, I mean, when you mentioned OpenJDK, I know there's been a massive exodus from OpenJDK to using Quarkus for containerization workloads. It works much better, and I just wondered if there was a parallel. But yeah, maybe it's an interesting project. Well, thank you very much, and I'm glad that your first LCA experience has been mostly smooth running, which is brilliant. We do have lunch now, and so we're taking a bit of an extended break. Please go and hydrate yourselves and get some kai, that's food. And we will see you back in here at, I've got to find my schedule, at 1:30 Australian Eastern Standard. I think I got that right. And we'll be talking with Fraser Tweedale about change owns and systemd containers and user namespaces. Thank you very much.
Thanks for coming along, everyone.